Hello everybody. In this video we're going to pick up exactly where we left off in our conversations about equations for lines and planes in 3-space. And our conversation last time left off with a discussion of lines, more or less. We discussed the equations of lines, both the vector and parametric forms, and we left off on a discussion on the distance from a point to a line. The other object we want to try to characterize via some sort of an equation or equations is going to be the equation for a plane. And so just as we did for a line, we're going to sort of draw a plane, identify all the key characteristics we've come up with, and then see if we can't sew them together in some reasonable way. We're going to give a plane a name. We're going to call it M. And recall that the key components for a plane are two things. One, a normal vector, which we might call n, given component-wise as capital ABC. And a normal vector can move around. We could have a normal vector over here, or down here. And so if we want to restrict where the plane lives, just like for a line, it's sufficient to say that the plane passes through a very specific point. And so if we were to draw a picture here, we might have something like the following. Here's a point P naught. And we suppose that it lives on this plane. Then this plane not only contains this point P naught, but a normal vector n, in this case, points straight up because we've drawn our plane flat. And this plane M is then characterized by all points, say P, given as arbitrary x, y, z's, such that this p-value, this point, lives inside the plane. So sort of like the setup for the line. And so what we can see is that sort of the correct way to view this is that this is the set of all points p, such that if we draw a vector connecting p naught to p, and we look at the vector p naught p, we ask that such a vector for any given p in the plane M, we ask that this vector be orthogonal to the normal vector n. And as long as we find points P where this vector is orthogonal to n, it'll have to live somewhere in this plane. That's the most important part of this, is that this vector P naught P is orthogonal to n. That's the defining characteristic of a plane. You take a point P naught, and then you have a normal vector, and your plane M is all points such that this orange highlight statement is a true statement. And because that's sort of the paramount object of interest here, we can unpack that a little bit. Clearly, if this vector is orthogonal to n, then what we're asking is that the dot product be equal to 0. But if n here is written component-wise as ABC, and p naught p is written component-wise as these difference of coordinates, then the equivalent formulation for the dot product here is the dot product of these two vector component vectors, where if we compute this dot product, it simply applies ABC to the respective coordinates. And so oftentimes what people will say is that you can give a plane in a variety of different ways. For example, this form is sometimes called the vector equation because it's made up of vectors. This form is sometimes called the component equations. And so these sort of serve as your vector and, say, parametric type equation differences for lines. And oftentimes, if you were to distribute all of the ABC and consolidate all your constants and pull it to the right, sometimes you'll see planes written this way. AX plus BY plus CZ is equal to D, where D is exactly those constants we pulled over to the other side. Sort of a neat trick to sort of characterize what's going on here is that the x, y, z right here are always variables. And the a, b, c, those come from the normal vector. And the constant here is encoding a combination of the normal vector along with the point in question. And so this can be a quick way to draft up the equation of a plane. So let's take a look at a quick example. Here we have find the equation of a plane going through 3 points. We sort of did this before when we were learning about the cross product. 3 points to find a triangle, and triangle lives in a plane. There, our goal was to find a normal vector to the plane, and here we're going to do that. In addition to finding the normal vector, we're going to steal one of these points and then build out the equation of the plane. So for starters, let's pick, say, we'll observe that we can compute AB. That's going to be the vector 2 minus 0 is 2, 0 minus 0 is 0, 0 minus 1 is negative 1. And we can compute, say, AC. This is going to be the vector 0, 3, negative 1. So, if we take the cross product, we know that the cross product, since each of these vectors live in the desired plane, their cross product will be orthogonal. So this is orthogonal to the desired plane. Well, that's fantastic, because that's giving us a normal vector to the plane containing these 3 lines, or these 3 points. So let's go ahead and compute this. Note that AB cross AC is equal to the determinant of I, J, K, along with AB, which is 2, 0, negative 1, AC, 0, 3, negative 1. So this is going to give us the vector 0 minus minus 3, that's positive 3. Negative 2 minus 0, that's negative 2. And 6 minus 0 is 6. So this is our normal vector. And what we need is a normal vector along with a point in the plane. Traditionally, I like to go with the components equations. That's what I really like. This shouldn't be equations, it should just be equation. And so writing it out that way, we'll say, thus, the plane is given by, in this case, we have 3 times x minus the x-coordinate plus negative 2 times y minus the y-coordinate plus 6 times z minus the z-coordinate is equal to 0, where we'll remind ourselves that 3, negative 2, and 6 are those coefficients. Those are coming from the normal vector. And then now we'll take any one of these 3 points will work. But say we take, let's go with A. It might be the easiest. So we'll go ahead and put 0, 0, 1. And we'll remind ourselves that this point, and this point came from that point. And of course, you're welcome to simplify this if you'd like. Perfectly reasonable. And so an equivalent formulation is 3x minus 2y plus 6z equals 6. It's a perfectly reasonable equivalent formulation. So these are the equations for a plane. But continuing the conversation of a plane, we can talk about lines of intersection. So we'll introduce this by observing that just as lines are parallel, if and only if they have the same slope, or equivalently within this conversation, the same tilt, what we're going to say is that 2 planes are parallel if and only if their normal vectors are parallel. Recall, of course, that the parallel nature of 2 vectors implies that they're scalar multiples of one another. And so the idea that we have here is that if I have one plane living up here, it has a normal vector, and I have a parallel plane, it has a normal vector, and the observation is that these two normal vectors are scalar multiples of each other. They're parallel. I should make a note here, by the way, that being scalar multiples of one another does not imply that they have to point in the same direction. For example, if I took this, I can twist it, and what we see here is, again, still two parallel planes, but the normal vectors point in opposite directions. So when it comes to two vectors being parallel, that just means they're scalar multiples of each other. They might very well point in different directions if that scalar, for example, is negative. So that's what parallel planes do. We will note here that two planes that are not parallel will always intersect in a line. That much we can see, for example, by drawing a vertical plane, and then we can draw a horizontal plane. And we see that when we do that, in fact, they do intersect at this line sitting here in the middle. Interestingly, however, we might observe that if I had a normal vector for that plane and a normal vector for this plane, observe that this red vector coming out of the page here is actually orthogonal, I should say, to both of the normal vectors. So if this is n1, we'll zoom in here actually. If that is n1 and this is n2, then this line of intersection, V is orthogonal to n1 and n2. However, how do I take two vectors and then find something that's orthogonal to both of them? Well, we know that answer. It's literally the cross product. So as a result, we can answer questions like this. Here are two planes given by this equation and that equation. For starters, find a vector parallel to the line of intersection. We're going to find that V. Well, let's observe the following. Notice that n1, which is the vector where I will steal the coefficients on the first plane's equation, so that's going to be 3, -6, -2, is normal to M. And n2, which is going to be 2, 1, -2, is normal to n. So stealing the coefficients of x, y, z tells us the normal vector for the plane, and then by this argument up here, their cross product should give us a vector that points in the direction of v. That is, a vector that is parallel to the direction of that line. So what we see is that the desired vector is n1 cross n2. And it actually doesn't matter which order you do it. One order will give you a vector, say, pointing toward us here, and the other vector will give you pointing in the other direction, but both of them are perfectly reasonable vectors for defining the line of intersection. So if you do compute this, of course, it'll take some work, but if you'd like to check your work, the final answer here should turn into the vector 14 to 15. And so, if this is going to be the vector parallel to this line of intersection, now that we have a vector for that line, the question is, can we find parametric equations for the line? Well, we'll note that from 1, the vector 14, 2, and 15 is parallel to the line. So we'll say the desired line. But the two pieces of data we need for a line are, of course, a directional vector, we have that, and a point. As it stands, we have equations for m and n, but we don't have a point that lies on the line. So what we're going to do is find one. We need to find a point that lives on both planes simultaneously. There's a couple of ways to figure that out. You could take these two equations and you could solve the system. Solving the system of these two equations is actually going to yield an infinite number of solutions, specifically because the solution is this infinitely long line. So you can streamline it a little bit by, for example, forcing one of your variables to be a number, like say we can force z to be 0. And once we force z to be 0, then we can solve the system. So putting z equal to 0, we solve the system coming from, in this case, 3x minus 6y is equal to 15, and 2x plus y is equal to 5. And now this is a system that has two equations and two unknowns, and therefore it potentially has a unique answer. We get, when we solve that system, we get x equals 3 and y equals -1. So what that means is that the point 3, -1, 0 lives on the line of intersection, since it lives in both planes at the same time. Thus, the line is given by, we're going to find parametric equations using this directional vector and this point, and so the answer turns into x of t is equal to 3 plus 14t, y of t is equal to -1 plus 2t, and z of t is equal to 0 plus 15t or 15t, where we ask that t live between -infinity and infinity. Now, yes, I will note here that there's a lot of variety in these answers. This directional vector we had up here, any scalar multiple of that will work. We could shrink it, we could make it bigger, we could flip its direction. Either way, it'll be parallel to the line of intersection. And similarly, I chose to let z be 0 to solve this system. In theory, you could let x be 0, solve the system in y and z, and you'll get a different point. Or if you let y be 0, get a different point. Or you don't have to let them be 0. You could let z be 5 if you want, and then that'll simplify this to a different system. The only thing that's going to happen is you're going to get a slightly different point on the line, which means, yes, this equation, these parametric equations are going to look different, but they form the same line either way, so it's all kind of irrelevant. One of the next questions we're going to investigate is, here we talked about planes intersecting planes. We could take up questions of, for example, lines intersecting lines, but you can imagine in 3-space, it's very unlikely that two lines will intersect, especially if they're what's called skew lines. However, what's more likely to occur is if a line passes through a plane. That's exactly the setup we have here. We have a line L given parametrically here, and we have a plane here. And the question is, where do they intersect? Of course, visually, this makes sense. This might be our plane M, and we might have a line going through it like this. And the question is, what's that point? That's what we're interested in. Well, it turns out the answer to this is fairly straightforward. X, y, and z are each functions of t, but they are coordinates for x, y, and z. So if we just take those coordinates and substitute them into the plane, then we're going to have one giant equation with only t as its variable, solve for t, and that gives us the parameter that indicates this point. So in this case, we're going to say, by substitution, we solve, and we're going to look at 3 times 8/3 plus 2t plus 2 times negative 2t plus 6 times 1 plus t equals 6. This is, at this point, just pure algebra. Distribute your coefficients, collect all the like terms, solve for t. I'll let you work through those details, and the answer you should get is that t is equal to 1. So, the point of intersection is whatever x, y, I should be careful with the way I write this, whatever x of t, y of t, z of t is when you evaluate it at t equals 1. And if you plug t equals 1 into these equations, you'll see that you'll end up getting, in this case, the x-coordinate is 8/3 plus 2, so it's going to be 8 plus 6 is 14/3. Then we're going to get negative 4, then we're going to get 3. And so it turns out this point is exactly this triple, x, y, z, in 3 space. So we can intersect planes and lines, that's not too bad. However, one topic we talked about for lines, but we haven't talked about for planes, is the distance from a point to a plane. Oh, I just realized I typoed. Okay. For those of you following along at home, no doubt you noticed that this should not be a 1. That I typoed. That should be a -1. Otherwise, there's no way these things are going to cancel in any nice way. So let's fix that real quick. -1. That will change these computations. So let's erase those. And we realize what we'll get is 8/3 minus 4. That's going to be 2/3. Then we should get a positive 2, and then we should get a 0. There you go. That's better. Okay, so getting back to what we wanted to do, we learned how to compute the distance between a point and a line. So the last thing we'll undertake here is the distance from a point to a plane. It's a very similar question, but it's sort of a little more difficult to answer. So here we have, for example, a plane. Well, let's actually just draw it not up here. Let's draw it right here just so we can see it all. So let's take a plane M. This is our plane M. We're going to suppose that it has a normal vector. Well, okay, let's just say straight up there's a point, say S, living over here. And we'd like to know the distance from S to the plane. Now, the same thing with the line. If I take the distance all the way over here, that's going to be longer than, say, over here. The only difference is where there's in a line, there was really only sort of one line to compare distances to. Here we have all sorts of directions we can go. But sort of the correct answer is still going to be the quote-unquote dropping the perpendicular. But we have to be a little careful with how we do that, because if I just drop the perpendicular here, how does that relate to M in any way? M only has 2 pieces of data, a point and a normal vector, and I haven't related S to that normal vector in any way. So what we can do is, say over here, pointing up is my normal vector. What I want to do is I want to relate S's location to N. And we're going to suppose that we move the normal vector in such a way that it coincides here with our defining point P. And so if my plane is defined by P and a normal vector n, and I take a point S anywhere else, and I want to know its distance to M, I relate it to where the normal vector is, and what I can realize here is that in fact, if I look at the vector containing P and S, what I see is that this is a right angle as well, and therefore this distance and this distance, so maybe I'll actually do this in different colors. We'll highlight it maybe. So what I'm noticing is that this distance right here and this distance right here are actually equal. And as a result, the distance from S to M is instead computed by calculating this distance. But what is this? This is just going to be, if I look at the vector from P to S, this is just the scalar projection of this vector onto N. That's what this distance right here is. This is just the scalar projection of PS onto N. And that's something we know how to compute by using a dot product. So that becomes the formula. The distance from S to the plane M, otherwise known as the d of SM, is going to be equal to the scalar projection of PS onto N, and we have a formula for that involving the dot product. It's the magnitude, or the absolute value, of the vector PS dotted with the unit vector pointing in this direction, which is just going to be n over the magnitude of n. So we can do a quick example here. If I wanted to take this distance to the distance from that point to this plane, we might note that the vector n, taken to be component-wise 3, 2, 6, is normal to the plane. So we'll also say, note that we need to find a point P on this plane. There's a couple of ways you can go about figuring that out. Sometimes it just kind of sort of is given to you via inspection. For example, we'll observe that if x is 0 and y is 0, or let's do, well, I guess they're all divisible, so it doesn't really matter which way we do it. Let's keep it consistent, and let's go with x is 0, z is 0. Well, let's write this down. Note that if x is 0 and z is 0, then y is equal to 3. So the point 0, 3, 0 is in M. We'll say as in the plane. So now we have a P, we have an S, we have an N. We now have the ingredients to compute this distance. So we'll observe that the vector connecting P to S is exactly going to be the vector 1 minus 0 is 1, 1 minus 3 is negative 2, 3 minus 0 is 3, 1, negative 3, 3. And we need to now compute the magnitude of N. So the magnitude of N is equal to the square root of 9 plus 4 plus 36. That's going to be the square root of 49, which we know is 7. So the distance from S to the plane, because I didn't actually give it a name, is equal to the magnitude of the vector 1, negative 2, 3, dotted with the vector n over its magnitude. So that's going to be 3 over 7, 2 over 7, 6 over 7. And if we want to compute what this turns out to be, there's some fractions going on in there, and you can verify at home that this is going to be the absolute value of 3/7 minus 4/7 plus 18/7, which boils down to simply 17/7, and that becomes the distance we're looking for. So again, it just sort of boils down into a data collection phase and then finally using the correct formula. But it all comes from the scalar projection. And finally, for this conversation, we'll note something about the angle between two planes. Notice that when I drew, for example, this picture all the way up here, I drew these planes in such a way that they were orthogonal to one another. That doesn't have to be true. For example, you might very well have one plane be sort of tilted over here, and you might have another plane that's not so tilted. And if we look at their intersecting line, we'll zoom in here. If we look at their intersecting line here, what you can see very clearly is that we have one vector sort of in this direction of that plane, another vector in the direction of that plane, and then the angle between those is going to be what we'll define as the angle between two planes. However, if we relate that to normal vectors, we see that exactly an equivalent formulation for this picture is that if instead of using these two vectors, we used actually, I guess the correct observation here is that in some sense, these vectors are sort of acting as twisted normal vectors for the other plane. If this picture is confusing in any way, maybe it's too small to do it justice, there's a really nice picture in the book that is accessible as well, but for the purposes of applications, what we need to know is that the angle between two planes is going to be defined to be the acute angle between their normal vectors. And so the application of this is pretty straightforward. Here's two planes, so we'll say that their normal vectors are n1, which is 3, -6, -2, and the other vector, n2, is 2, 1, -2, respectively. So the angle between them is theta, which is cosine, well, we'll call it the arc cosine of exactly the formula we had way back earlier in the chapter. It's going to be the dot product of these two vectors over the product of their magnitudes. And so here you'd want to compute their dot products and their magnitudes. And if you do all that, this should turn into the arc cosine of 4/21. And this is a perfectly reasonable way to leave your answer. I'm confident that everybody can use their calculator to compute the arc cosine of this fraction. All in all, that's about what we want to talk about in section 11.5. I know it's a lot of content, but it's a lot of really, really important foundational content as well. So make sure you practice, review the material, rewatch some of the video if necessary, take a look at the homework problems, and if you have any questions, be sure to reach out. I'm more than happy to help. But otherwise, I will catch you all later.